Welcome to MarkScheme. Proof and identity. Everything you need made visual. Look at these two statements. On the left, 2x plus 4 equals 10. On the right, 2 times x plus 2 equals 2x plus 4. They both have an equal sign. But they are profoundly different kinds of statement. And telling them apart is the whole first half of this topic. The left one is only true for a single special value, x equals 3, and nothing else. The right one is true for absolutely every x you could ever put in. One is a puzzle to solve. The other is a fact you can prove. That's an equation versus an identity. And by the end, you'll prove one yourself. Watching the left side literally become the right. Here's exactly what we cover, straight from your syllabus. IB analysis and approaches. Standard level 1.6. Simple deductive proof, both numerical and algebraic. How to lay out a proof that works from the left-hand side down to the right. And the two symbols for equality and identity. Tick all four, and the subtopic is complete. Everything we prove uses only the algebra and index laws from 1.1. Nothing new assumed. So let's name them. The plain equal sign is conditional. It's a claim that holds only for particular values of x. Your job is to solve and find them. The identity sign, that 3-bar symbol, means identically equal. The two sides are the same expression, true for every single x. You don't solve an identity. You prove it. Here's the picture. Plot both sides of the identity. Y equals 2, x plus 4 in green, and y equals 2 times x plus 2 in gold. They are the exact same line. The gold sits perfectly on the green, coinciding at every point. That's what true for all x looks like. Not a crossing, a complete overlap. An equation is different. Its two sides are usually different graphs, and the solution is just wherever they meet. Here, the line meets the level, y equals 10, at one isolated point, x equals 3. Isolated crossings mean an equation. Total overlap means an identity. Before we prove anything, what actually is a proof? A deductive proof is a chain of logic. You start from something already known to be true, a definition or algebra you can trust, and you take valid step after valid step until you arrive at the target statement. Each arrow is a move nobody could argue with. And here's the golden rule that keeps a proof honest. You never start from the very thing you're trying to prove. If you assume it's true and shuffle it around, you've proved nothing. That's circular. A proof flows one way, from the known to the target. Now, the main event, the left to right method, the single most important layout in this topic. We'll prove that x plus 3 squared minus x minus 3 squared is identically 12x. The plan. Take the left-hand side and only the left-hand side and simplify it step by step until it turns into the right. We never touch the answer and drag it back. Step 1. Expand each bracket. X plus 3 squared is x squared plus 6 x plus 9. X minus 3 squared is x squared minus 6 enter x plus 9. Watch the left side morph into its expanded form. Step 2. Remove the brackets. Being careful with that minus sign. It flips every term in the second bracket. Minus x squared plus 6x minus 9. This sign flip is where marks get lost. So it's on screen in full. Step 3. Collect like terms. The x squared and minus x squared cancel completely. Plus Nikin and minus 9 cancel too. 6x and another 6x survive. And 6x plus 6x is 12x. The left-hand side has become 12x, which is exactly the right-hand side. The two sides are identical, so the equal sign earns its promotion to the identity sign, and we lock it in. Let's do a numerical proof, a proof about numbers. Claim: add any two consecutive odd numbers, and you always get a multiple of 4. You might test it. 5 plus 7 is 12, which is 4 times 3. Nice. But a checked example is not a proof. It says nothing about the cases you didn't try. We need every case at once, so we go general. Any odd number can be written as 2n plus 1. The next odd number is 2 more, 2n plus 3. Add them. The two n's give 4n, and 1 plus 3 gives 4. So we have 4n plus 4. Factor out the 4, and it's 4 times n plus 1. A multiple of 4, guaranteed, for every integer n. That covers all cases in one line. Proven. Now, a purely algebraic proof, again in full. Prove that n squared plus n is even for every integer n. The clever first move is to factorize. N squared plus n is n times n plus 1. Suddenly the structure is doing the work for us, because n and n plus 1 are consecutive integers, 2 whole numbers in a row. And of any two consecutive integers, 1 is always even. So the product n times n plus 1 always contains an even factor, which makes the whole product even. Therefore, n squared plus n is even for every integer n. Notice each line is a justified step. And we finish with a clear concluding statement. Let's raise the bar. Prove that n cubed minus n is divisible by 6 for every integer n. This looks harder, but the same idea from a moment ago cracks it wide open. Start by factorizing. N cubed minus n is n times n squared minus 1. And n squared minus 1 is a difference of 2 squares. So it splits into n minus 1 times n plus 1. Line them up in order. Now look at what we've got. N minus 1, n, and n plus 1. 3 consecutive integers. 3 whole numbers in a row. And a row of 3 has guaranteed structure. At least one of them is even, a multiple of 2, and exactly one of them is a multiple of 3. So their product carries a factor of 2 and a factor of 3, which means it's divisible by 2 times 3, 6. Therefore, n cubed minus n is divisible by 6. And we finish with the concluding line. Let's reinforce the left to right method with a second identity, shorter this time. Prove that n plus 1 squared minus n squared is identically to n plus 1. In words, the gap between two consecutive square numbers is always an odd number. Same plan. Take the left-hand side alone and simplify it down to the right. Expand the first bracket. N plus 1 squared is n squared plus 2 n plus 1. Drop the brackets. There's just a minus n squared trailing. And now, the n squared and the minus n squared cancel, leaving 2n plus 1. That's exactly the right-hand side, so the equals earns its promotion to the identity sign. Left equals right, as required. One last idea, and it's the mirror image of everything so far. We said one example can never prove a statement that claims to hold for all cases. But watch the flip side. Take the claim. Every prime number is odd. To knock it down, I don't need a general argument. I need just one prime that isn't odd. And there it is. N equals 2. 2 is prime, and 2 is even. That single counterexample destroys the claim completely. It is now false, full stop. So hold the two ideas side by side. One example proves nothing about a for all statement. But one counterexample is a complete disproof. To disprove something universal, you only ever need to find one case where it breaks. Now the exam craft. Other channels skip. First, the command word. Show that and prove that both want a full deductive argument, not a check, and hence is a gift. It means use the result you just found, so don't restart from scratch. Second, state each step, and always conclude. A line like, therefore left-hand side equals right-hand side, as required, is itself worth a mark. Third, the answer given trap. When the target is printed on the paper, examiners want every honest step. You can't skip to the printed line. And fourth, set your notation up cleanly. Even is 2n, odd is 2n plus 1, consecutive integers are n, and n in plus 1. Clean structure earns method marks even if your algebra wobbles. And fifth, remember the asymmetry. To disprove a for-all claim, you give a single counterexample. But to prove one, examples are never enough. You need a general argument. Finally, the four traps. 1, and it's the big one, circular reasoning. Starting from left-hand side equals right-hand side, and simplifying both to 0 equals 0. That assumes exactly what you're meant to prove, so it earns nothing. Work one side down to the other instead. 2. Thinking one example proves a general statement. Testing n equals 2 proves only the case, n equals 2. 3. Doing all the algebra correctly, but forgetting the concluding line. Always finish with as required. And 4. Proving it for a general n, but never actually stating the claim. Holds for all integers n. Name the domain out loud. Because for every integer n is part of the statement you're proving. Dodge these 4 and proof questions are some of the most reliable marks on the paper. And that's SL 1.6, fully covered. The difference between an equation and an identity. The two equality symbols. How to lay out a clean left to right deductive proof. A whole ladder of numerical, algebraic, and divisibility proofs done in full. A second identity. And the flip side. Disproof by counterexample. Next in the course, the binomial theorem, where proof and pattern meet. For more, that's MarkScheme.app. See you there.